Okay, now we will do some problems based on the linear transformation. This here we do this problem. Um uh, Let B be a finite dimensional vector space. Let B be a finite dimensional finite dimensional vector space. T is a linear mapping LV, V to V, right? So the following statements are equivalent statements. Okay, so that the following statements, following are equivalent statements. So that the following are equivalent statements. Okay. Here, first part, kernel of T equal image of T when is happen be T squared equal 0 and null of T equal rank of T. Right? Null of T equal rank of T. Okay. Null of T equal rank of T. You want to prove A to B, next you want to prove B to A. It's equivalent, right? Let here B be a finite dimensional vector space. T is a mapping from LV to V. So that the following statements are equivalent means, suppose you assume that A is true, then you want to prove that B is true. Suppose you assume that B is true, then you want to prove that A is true. There are two parts there, right? You want to prove. Let be a finite dimensional vector space. Let B be a finite dimensional vector space. And T is a linear mapping N V to V, right? Suppose that you assume that this one is true. Suppose that kernel of T equal image of T. If you take one of the element X belong to B, right? Therefore, X belong to B means T mapping from B to B. Therefore, T of X also belong to image of T, no? T of X belong to image of T, but this image of T equal kernel of T. Therefore, you have now T of X belong to kernel of T. Therefore, this T of X equals 0. This T of X 0 means 0 V. Okay, 0 means this here composition function T composition X equals 0 V. So you can write this T squared, no? T squared of X equals 0 V. Now you want to show that T squared equals 0. Okay, and null of T equal rank of T for this part, right? You take dimension of kernel T equal null of T, no? Dimension kernel of T equal dimension of image of T from the assumption. Here, kernel of T equal image of T, take both side dimension, we get this one. Dimension kernel of T, you know, this dimension of kernel of T, another name is null T. Dimension of image of T, another name is range T. Right? Rank T. Okay. Rank T. Okay. Now for a converse part, now we prove A to B. Next, we want to prove B to A. It is proof for the A to B. Now B to A. Conversely, suppose that conversely suppose that there are two conditions: t squared equals 0, right? T squared equals 0, and null t equal rank t. Okay, null t equal rank t. Now you want to prove it, image of t equal to kernel of t. Okay, let y belong to image of t. You take one of them and image of t. Y belong to image of t means you can write here y equal t of x. Therefore x belong to b, no? For some x belong to b. X belong to b because b to b. Now you can take both sides mapping t of y, here t of x, but t of x means t squared of x, but you already know that this t squared of x assumption 0 is 0, therefore t of y 0, the t of y 0 means t of y, right? T of y 0 means, right? T of y 0 means this y belong to kernel of t, therefore we already take y belong to image of t. Now we prove y belong to kernel of t, therefore this image of t subset of kernel of t. Okay, image of t subset of kernel of t. But you already have, right? You already have this condition, null of t equal rank of t, right? Null of t equal rank of t. Null of t means another names dimension of kernel t, right? Dimension of kernel t equal dimension of image of t. For rank t, dimension of image of t. Then with this both condition, you can tell here kernel t equal image t. Kernel t equal image t. Image of t subset of kernel of t, and this rank of dimension kernel of t equal dimension image of t. Therefore, kernel of t equal image of t. Okay. Right. Next question. Next question. Let B be a finite dimensional vector space let B be a finite dimensional vector space prove that if T B to W is a linear mapping, T B to W is linear, be linear, and the condition image of T equal image of T squared, right? Image of T equal image of T squared if and only if kernel of T equal to kernel of T squared, right? Kernel of T equal to kernel of T squared. Okay, for this part, let B be a finite dimensional vector space V be a finite dimensional vector space. Okay, V be a finite dimensional vector space. First, you assume that T is a linear one and image of T equal to image of T squared. Suppose that T be a linear mapping. Suppose that image of T equal image of T squared. Now you want to show that kernel of T equal kernel of T squared. Okay, kernel of T equal to kernel of T squared. If take x belong to kernel of T. Suppose x belong to kernel of B means T of x 0. Okay, C of x 0. Now you take both sides T mapping again. T of x. T of 0 by the linear transformation 0. You put here V, here W. Here W, sorry. Here W. Then C. Okay, otherwise, okay, no problem. See here. Okay. T of 0 equal to 0 by the linear transformation. This one true. Then this one is T squared of x equal to 0. T squared x 0 means this x belong to kernel of T squared. Okay, x belong to kernel of T squared. Suppose you take x belong to kernel of T, you prove it x belong to kernel of T squared. Therefore, this kernel of T subset of kernel of T squared first. Kernel of T subset of kernel of T squared. But you want to show that kernel of T equal kernel of T squared. For that one, still we didn't use this fact. Okay, now we use this fact to prove the kernel of T squared subset of kernel of T. Since image of T equal image of T squared, then dimension of image of T equal dimension of image of hypothetic dimension T squared. Now you have the Rangeley theorem. What is the dimension of kernel of T? Dimension of kernel of T equal here dimension of B minus dimension of image of T. No, dimension of B minus dimension of image of T. But this dimension of B, dimension of image of T equal dimension of image of T squared. Dimension of image of T squared. Okay, dimension of image of T squared. Now, what is the meaning of this one? This one means dimension of kernel of T squared. Here, dimension of kernel T. Okay. In the previous question, right? In the previous question, you already know that in the previous question, you prove that image of T subset of kernel of T, and you have the condition dimension image of T equal dimension of kernel of T. From this both, you can tell this image of T equal kernel of T. Like that here, kernel of T subset of kernel of T squared, but dimension of kernel of T equal dimension of kernel of T squared. Therefore, this kernel of T equal kernel of T squared. Like a previous question, right? Kernel of T equal kernel of T squared. Now converse part, because the converse also true. Converse part. Conversely suppose that this kernel of T equal kernel of T squared. Therefore, you can take the both side dimension. Dimension of kernel of T equal dimension of kernel of T squared. Now you can use the dimension theorem again. This the Rangeley theorem. Dimension of image of T. Okay, dimension of image of T. Dimension of image of T equal dimension B minus dimension of kernel of T. Okay, dimension kernel of T. But you have dimension of kernel of T equal dimension of kernel of T squared. Therefore, dimension of V minus dimension of kernel of T squared. Okay, suppose dimension of V minus dimension of kernel of T squared means dimension of image of T squared. Now we prove dimension of image of T equal dimension of image of T squared. Now, this was first condition. Now your claim is you want to prove that image of T equal to image of T squared. Okay, image of T equal to image of T squared. Now you take y belong to image of T squared. Then you can write y equal for T squared mapping for some values x belong to B. For some x belong to B. Okay, this one y equal T of x. Okay, T of x. But this x, T of x belong to B, no? T of x belong to W, no? T of x here, right? You know, T here B to W, T is a mapping, no? Just wait. Here T is a mapping V to W, no? T is a mapping V to W. T mapping V to W. Okay. Okay. Now, right. Now you can tell here, what is the T of x, right? T of x belong to image of T, no? This one also image of T. You put another name as a y1 or something. Then again, T of y1. That one also image of T. Is it okay? It was image of T. Is it okay? Therefore, image of T squared subset of image of T. From this condition, dimension image of T equal dimension image of T squared, that condition image of T squared subset of image of T, therefore from both image of T equal image of T squared. Right, image of T equal image of T squared. You know, Bayesian belong to image of T for a T squared mapping or T mapping, because T of x also one of the image. Again, take the T mapping, then that one also one of the image. Therefore, Y belong to image of T. Therefore, image of T squared, subset of image of T. What you previous condition, dimension image of T equal dimension image of T squared. From this both dimension, from this both image of T equal to image of T squared. Right. Now another exercise. exercise number 3. Let B1 up to Bn be basis of B. Let B1, B2, and so on Bn, right? Be basis of B basis, right? Basis of B. Let T B to W, B to B, LB, B to B, be a linear map. Linear map. There are two parts. You want to prove it. First part, if T of B1 equal V2, T of B2 equal V3, and so on, T of Bn minus 1 equal Bn, and T of Bn equal T of Bn equal V1, then T of M equal IB, identity mapping. B part, you want to take these conditions, you want to prove this T of M equal IB. If T of V1 equal V2, T of V2 equal V3, and so on, T of Bn equal 0, then T power M, this T power M equal to 0 mapping. 0. Right, these two parts you want to prove it. Okay. V1 up to Bn be basis of B. Let TV2 be a linear map. Then these conditions, T of B1 equal V2, T of B2 equal V3, T of up to T of Bn minus 1 equal Bn, T of Bn equal V1. Then you want to prove it T power M equal to identity map IV. If T of B1 equal V2 and T of B3, T of B2 equal V3 and so on, T of Bn is B1 is 0, then your Tm also 0. Okay, right. For a part, T of B1 equal V2, T of V3 equal V4, V2. So V2 equal V3, V2 equal V3, T of V4 to V3 equal V4, and so on. T of Bn minus 1 equal Bn, and in that is condition, T of Bn equal V1. T of Bn equal V1. Okay. T of Bn equal V1. And T of Bn equal V1. And T of Bn equal V1. Now you consider T of M. Sorry, here is N, no? Here N. M does not define N because up to N basis thathayano. Right. You don't give any definition for the m here. Therefore, introduction for m, therefore is n. Okay. Now you consider this one first. Tn of b, Tn of b1. This one you can write Tn minus 1. Is it okay? Tn minus 1 T times v1. Tn minus 1 T times v1 means v2. This one implies Tn minus 2 T times v2. This T times v2 again Tn minus 2 T times v2 means v3. Right? This Tn minus 3 T times v3 means continuous process. N minus 3 T of v3 means v4. Right? And so on. You can move it, right? Right? You can move it. Last you get, right? The last you get suppose here, here n minus 2 and n minus 3, n minus 4, sorry, n minus 3, then you can get again, you can get n minus 4. And here this number n is increased. Suppose you take t n minus n minus 1, right? N minus 1, here n. It is sure t of b n, because n cancel 1 power. About t of bn, okay? N minus 1, okay? T of n minus 1. Here bn, okay? N minus 1, bn. Therefore, t of bn. But or define t of bn equal b1. T of bn equal b1. Right? T of b1 equal b1. Okay? Thus, you can write T of n b I. Suppose you take here b2, then you get here b2. Therefore, bi. For I range from 1 to n. Since T is linear, therefore T power n you can write composition of T and so on up to n is linear. Okay. T power n also linear, because T is linear means T power n also linear. The composition of two linear functions is linear, no? Therefore, it's linear. We have some proofs, right? We in the chapter we have some proofs. Suppose T of n is linear, then you have the unique representation for this part. Okay. Since there is only one linear transformation, there is only one linear transformation, unique one. There is only one linear transformation, on V. Right? V to V, no? Like V to V. Maps, that maps Vi to Vi. V1 to V1, V2, V2, V2. Here the range of this one to In. Right. That means here T of n times Vi, right? T of n times Vi. Okay, T of n times Vi. Vi you can write IB of Vi. So identity mapping, IB of Vi. This implies for any values of Vi, Tn equal IV. Tn equal IV, identity mapping. Tn equal IV. Okay, Tn equal IV. For a B part, now B part, Tn equal IV. B part, you want to show that Tn equal to 0. B part, you want to show that Tn equal to 0. Right? B part, you want to show that Tn equal to 0. B part. Here T of V1 equal V2, T of V2 equal V3, and so on. T of Vn equal 0. T of Vn equal 0. Okay. Okay, now for the previous part, your T of Bn equal B1. The same idea we now again do. You take first this T of n. Okay, T of n B1. This one T of n minus 1 B T of n minus 1 T of B T of B1, but T of B1 equal B2. About this of T of n minus 1 B2 again T of n minus 2 T of B2, but T of n minus 2 this one B3, right, and so on. Suppose n minus 1 into Bn. We have for this values n and cancel, you get T of Bn, but previous part T of Bn equal V1. Now T of Bn, now we T of Bn equal to 0. Okay, now T of Bn equal to 0. Therefore, I is from 1 to n. Therefore, Tn for any values of Bi, suppose you take Bi equal 0, I take the value 1 to n. Okay. Because you know here Tn of B1 0, Tn minus 1, that means here, yeah, Tn minus 1, Tn minus 1 T means again T of B1 again this one also 0, this one also 0, then this one also 0, then this one also 0. Therefore, the Tn of for any values of Bi is 0. Right? Previous part, this one equal to here your B1, therefore you get suppose Tn of B1 equal B1. This value again get. Now for this part, T of n of B1 equal to 0. Therefore T of n of B1 equal to 0 means T of for here T of n minus 1, T B1, this one also 0, this one also 0, this one also 0, all are 0. Then for a T of n, for any values of Bi 0. It means here, suppose you take here arbitrary V2, okay, you take V2, T of n V2, then T of into Tn minus 1 V2, Tn minus 1 into T of B2, Tn minus 1 into T of B2, right? T of B2, you can write Tn minus 1 B1, then you get this formula. Like, therefore, the all values are 0, okay? Okay, these are the some excess of the linear transformations, okay?